Friends, in our today's lecture, we will solve two examples. Example number 1.11 and 1.12. Now, in this example 1.11, it is given that in a three-dimensional coordinate system, that is x-axis, y-axis and z-axis, a cube is placed. You can see a cube is placed, and this cube is placed in such a way that its left side face is at a distance a. Even length of the cube is also a. Given that there is an electric field along the x-axis, you can see in this data that electric field is along the x-axis and it is given by alpha x raised to 1 by 2. So this is the electric field. Now this type of electric field is non-uniform electric field. Why? Because this electric field changes according to distance x. You can see there is x raised to 1 by 2. So as the distance changes, electric field also changes along the x-axis. Here alpha is a constant and its value is given in SI system of unit. Given that the electric field, its component along y and z axis is 0. So this says that electric field is totally along the x-axis. Now A, that is length of the cube, that is 0.1 meter, and here we need to find the flux linked with the cube as well as the total charge enclosed in a cube. Now as you can see in figure, the electric field has only its x component, so it is along the x direction only, and so the flux is linked with the only two shaded surfaces of a cube. So we can say that out of 6 faces, the flux is linked with only two surfaces, left side surface and right side surface. To the rest of the surfaces, the flux linked will be 0, because for these 4 surfaces, the area vector, that is delta S, and electric field, they are perpendicular to each other, and we know that when these two are perpendicular to each other, the angle made will be 90 degree, and so cos 90 will be equal to 0, and so the flux linked with these surfaces is also 0, and so the total flux linked with the cube is only with its two surfaces, left side surface and right side surface, and so total flux phi is equal to phi L plus phi R. Now let us calculate the flux linked with the left side surface. We know the formula for the flux. Flux phi is equal to E dot S in vector form. Now let us see from the figure that where is electric field and where is S. So for left side surface, the electric field will be along x-axis only, because it is given in the data that electric field has its only x component, and area vector of this left side surface will be towards negative x direction. And so flux linked with this surface is given by EL as cos 180. Why angle is 180? Because electric field is along the right side and area vector is along the left side, and so angle made between these two vectors is 180. And so here cos 180 is taken, and we know that cos 180 is minus 1. So for this we'll put minus sign and EL into S as it is. Let us give this equation number 3. Earlier this equation we have to give number 2. Also equation number 1 is given here so that we can use it later on. So this was about the flux on the left side. Now flux on the right side surface. Again, according to the formula, it is a dot product of electric field and surface. But here angle made between these two vectors is 0. Let us see from the figure. You can see on this right side surface, electric field is given, which is along the x-axis only. You can see here, and the area vector for this surface is also along the x-axis. We know that area of any flat surface is along the normal to the surface. So if we draw the normal to this surface, then it is along the x-axis. And so as these two vectors are in same direction, the angle made between them is 0. And so here we have taken cos 0, and cos 0 is equal to 1, and so remained is ER into S. Now let us give this equation number 4. Now using equation number 3 and 4 in equation number 2. This is equation number 2. So we are going to use 3 and 4 in 2. Now in this equation 3 and 4, common is S. So we will take out this S common. So after putting these values, this S is taken out common and remained EL and ER inside the bracket. In next step, we will put the value of EL and ER. Now in a given condition, electric field is given. Let us see once again that given equation. So this is the given equation. Ex is equal to alpha x raised to 1 by 2. And so for left side surface, the distance of this surface from the origin is A. So here for this x, we'll put A as a distance for left side surface. Alpha is constant and its value is given. Similarly, for the right side surface, the distance x will be a plus a, that is twice of a. So from origin, the right side surface is at distance 2a. So we'll put this for right side surface. So now you can see here, for EL we have taken alpha a raised to 1 by 2 because distance is a for that surface, and for right side surface the distance is twice of a. So in place of x we kept 2a, rest of the things as it is. Now even in this equation you can see that alpha and a raised to 1 by 2 is common for both the terms. So alpha and a raised to 1 by 2 is again taken common. So what is remained inside? So if alpha and a raised to 1 by 2 is taken common from this first term, then remain is minus 1. You can see here this is minus, and if this is taken out then 1 is remained. And here in second term alpha and a raised to 1 by 2 is taken out, then remain is 2 raised to 1 by 2, that is root 2. So this is simple mathematical step, you can easily understand. Now we will put the values given to us. Here 800 is value of alpha, 0.1 is value of a, and area, surface area of a square is this, s is equal to a square. So we'll put that also, and after simple calculation you can get the value of flux. There will not be any difficulty in this calculation. So we get the total flux linked with that two surfaces. And so the flux linked with the whole cube is also 1.04 Newton meter square per coulomb. Now in part B we want to find the total charge also. So using the Gauss law, flux phi is equal to total charge enclosed by the cube upon epsilon naught, making subject q will get phi into E naught, and then using values we'll get the total charge also in coulomb. So here we complete this example, and now next example is example number 1.2. Now here in this example also the situation is similar, calculation will be also similar, formulas used in this example is also same as that used in example number 1.11. In this example we need to find the flux linked with the left side surface, that is this one, flux linked with the right side surface, that is this one, flux linked with the curved surface, that is this curved surface of a cylinder. Then we have to add this all flux, and so we'll get the total flux also. So we need to find the total flux linked with the cylinder, and then finally we have to find what is the charge enclosed in this cylindrical surface. So now let us understand first this figure. So if you will read the statement of this example from the textbook, you will find that for this right side surface, the electric field is along the right side, that is along positive x direction, and for left side, that is along the negative x direction. For this surface, the electric field is in that side. So now it is clear that for the right side surface, electric field is along this direction. Even for this plane surface, the area vector is also in this direction, and so the angle made between this electric field and delta S will be 0, and so here flux is linked. Similarly, for this left side surface also, electric field is in this direction and area vector for this is also in this direction. So here also the flux linked will be same as that on the right side surface. So it is clear that the flux is linked with both these surface will be equal. Now remained is this curved surface. Now we know that for any curved surface, the area vector will be normal to the curved surface at any point. So for that, here we have taken a small element of a curved surface. So for that curved surface, the area vector will be normal to this surface, and the electric field at this point where this small element is taken will be along this direction, that is along positive x direction. So angle made here is 90. So we can say that for the curved surface, the flux linked will be 0 because cos 90 gives us 0. Now if we have selected the small area element on this side, that is on left side, then also the area vector will be normal to the curved surface, while electric field on this side is towards left side. So again angle made will be 90. So it is clear that for the curved surface, the angle between electric field and area vector will be 90, and so the flux linked with the curved surface will be 0. So now let us see the calculation part. On the left side surface, flux linked is given by this formula E dot delta S in vector form, and I have written that C figure and I have explained the figure to you. Removing the dot product, we get E delta S because this condition which I explained to you. Both E and delta S are parallel, and if they are parallel then angle will be 0, and if angle is 0 then cos 0 is 1, and so simply we'll get E delta S. Now what is delta S? So we know that left side surface is circular like this. For a cylinder, this left side surface is circular in shape, and so area of a circle is pi r square. Now using the given values, electric field is given 200, value of pi, and radius r is given in centimeter. It was 5 centimeter. So when we put the value, we have to convert that in meters. So I have taken 0.05 meter and square is there. So after calculation, you will get flux linked with the left side surface is 1.57. Similarly, as I said, the flux linked with the right side surface is also same. So its value is also 1.57, giving this equation number 1 and this equation number 2, so that we can use these equations later on. Now B part, that is flux linked with the curved surface. I earlier told you that for the curved surface, flux linked will be 0. Why it is 0? So once again, as the area vector and electric field, they are perpendicular to each other, angle between them is 90 and cos 90 is equal to 0. And so using the formula of flux E dot delta S, removing this dot product, we have to put the cos theta, but theta is 90, and so cos 90 is 0, and 0 into anything is 0, giving this equation number 3. Now total flux or net flux. Total flux linked with the whole cylindrical surface is given by flux linked with the left surface, flux linked with the right surface, and the flux linked with the curved surface. So adding all this flux will get the total flux linked with the cylindrical surface. Now from equation number 1, phi L is 1.7, phi R is 1.57, both are same, and for the curved surface the flux is 0. So after addition of this, we'll get the total flux or the net flux linked with the cylindrical surface is 3.14. Now after obtaining the total flux linked with the whole cylindrical surface, we want to find now the charge. Now for that charge, we know the equation of Gauss law. It is flux phi is equal to total charge enclosed by the surface upon epsilon naught. Now making subject Q here, we get Q is equal to phi into epsilon naught. See, this thing we have done in the previous example also. So after putting the values, you will get the total charge enclosed in the cylindrical surface is this. See, here we have simply kept the values and calculated. So you will get this answer 2.78 into 10 raised to minus 11 coulomb. So students, I hope you get these two examples nicely, and still if you have any doubt related to these two examples, then you can contact me.